Hello Year 12 and welcome to the second video for our differential equations topic. Today we're looking at slope fields, and a slope field is a graphical representation of a differential equation. This is only going to work for a particular type of differential equation. Not all differential equations will be able to be represented this way. The ones that we're looking at are going to be differential equations that take the form of y prime equals some function of x, some function of y. So in this example here, we're asked to construct a slope field for this differential equation, and then to sketch some solution curves that are particular solutions, including one of them that passes through the origin. The other two, we can draw them wherever we like. So the first thing we do is we draw up a table of slopes, right? Like a table of values, but instead of just x and y, I need a variety of values of x and a variety of values of y. So this is much bigger than the sort of table of values we might use to help us sketch a curve. Right. So in this case, I'm going to look at x values from -4 to 4, with a difference of 1 between them, and the same for y, from -4 to 4. So if x equals -4 and y equals 4, I substitute those values into my differential equation to find the first derivative. X plus y, -4 plus 4 equals 0. So my slope at the point -4, 4, right, up there in the second quadrant, my slope, my gradient is equal to 0. That's a horizontal line. Okay, now, if I look at the point -3, 4, substitute those in, x equals -3, y equals 4, that's going to give me y prime equals 1. Okay, so we've got a 1 here. The same with -2, 4, gives me a gradient of 2 in this case. And then I continue that quite a few times to find all of these slopes. You can see that this is going to be a pretty laborious, time-consuming operation. And it's fairly inexact as well, because I'm only investigating the slopes at, over a pretty limited domain. Anyway, now that I have quite a few slopes there, quite a few gradients, I can start to graph those. So we draw up a number plane, and it helps to have a grid here because we need to place them fairly precisely. So there's my number plane. I haven't put numbers in because you're going to see it gets fairly crowded, but each one of these grid spacings is going to represent one unit. So let's start here at the point -4, 4, up here in my second quadrant, -4, 4. The slope there is 0, so I'm going to put a small line there that has a gradient of 0. For the sake of sort of efficiency, simplicity, I can see I've got this row of zeros, this line of zeros running down here. It's probably easiest to draw all of those at once. Okay, so now I'm at the point -3, 3, another one there. So I'm going to put all of those in. Where I have a line that connects points of equal gradient, that line's called an isocline. Sometimes that's helpful, sometimes less so. But you can see we clearly have an isocline here along this pathway, which is along the line y equals -x. Okay, so having done that, let's have a look at some other points now. I'm at -3, 4. It's got a gradient of 1. Gradient of 1 looks a bit like this. So I'm going to put all of those in. Then, slowly, one by one, I'm going to put all of these other gradients in. Little tick marks everywhere on my number plane, so I can see those slopes everywhere. That takes a little while. It takes a little while in PowerPoint, let me tell you. So, we start to get a bit of a picture there of the way that all of my slopes are related to each other. So we get a sort of curving, sweeping pattern here, and a much sort of sharper curve here, and this line running down the middle. This is a special isocline along this pathway here, where the gradient of the isocline is the same as the gradient of all of the points that it's joining together. So all of those little lines are pointing to each other in a straight line. Yeah, it's a bit of a special case. Don't worry too much about it, but you can see that sort of looks significant. Now, because that's a significant one, I'm going to use that as one of the three particular solutions or solution curves that I've been asked to draw. Right, so I'm going to draw one along there. It's a good one. It's important to keep in mind that no point can have two gradients, and so none of my solution curves can ever meet or cross, but we can have asymptotes where they sort of converge, where they get very close together. And this particular line here is one of those asymptotes. So let's look at another one now. I'm going to start down the bottom here somewhere. And what I need to do is to just sort of freehand in a curve. Now, it doesn't have to go from corner to corner. It won't necessarily go through the intersections, through those particular points. But wherever I am, I need to have a gradient that's somewhere between the gradients on either side of me. So I'm going to start down the bottom and draw a curve that runs up through here. Okay, and you can see that curve there, the gradient of any tangent there is pretty similar to the gradients nearby. So now I've got two solution curves. I was asked to put one through the origin as well. So it's got to go here. See, the gradient at the origin is 0. Over here on the right, it becomes positive and curves upwards quite sharply. On the left, well, there's sort of limited detail, but somewhere in between, say this point and this point, the origin and -1, 0, right? It goes from being 0 to being -1. So I should move into a gradient a bit like that up here. And I'm going to be using, whoops, I've gone off to the right to begin with. Never mind. So you can see that I'm sort of following the gradients, right? At any point along that curve, the gradient is fairly similar to the gradients indicated by the slope field nearby. So that's one half of it, and the other half is going to curve up here with that asymptote. It's not a perfect curve, you know. I've only drawn this using some pretty rough software, but you can see there I have 3 solution curves. Now it's pretty hard to determine what the equation of those lines are, but this one here, the first one we drew, that straight line, we should recognise the equation of that line is y equals -x minus 1. And you could test that to see if that's a solution, and it should satisfy our differential equation. So that's what we're asked to do for slope fields. It's a slow, painful process in many ways, and still fairly inaccurate. But it's an interesting way to visualize all of these solutions. And we can see that the solutions might look quite different to each other at different points on our slope field. Rightio, that's it for this exercise. Let's just go over the things we've looked at. Table of slopes can be used to construct a slope field. Particular solutions can be sketched on that slope field by drawing a curve with a gradient that's similar to all of the adjacent points. A line that connects points of equal gradient is an isocline, and that doesn't have to be a straight line. Sometimes it is, and sometimes that's significant. But it's not always a straight line, and it's not always significant to us. Particular solutions can't intersect, right? Because every point has a unique gradient. Rightio, that's it. Our next video is separable differential equations, and it's really quite a very important exercise, that next one. If you've got any questions, make sure you jot them down so you don't forget and ask me, and I'll see you in class.